Welcome to CS1104 Computer Systems. This is the Unit 4 lecture part 2. During this lecture, we're going to take some of what we learned about in the previous lecture, which was the idea of sequential logic and the fact that what makes sequential logic different is this idea that it allows us to feed back information that I've put into the circuit, back into the circuit, for the purposes of maintaining statefulness. So once I put the data in there, by feeding it back, continuously feeding back, I can hold it in there. So the information doesn't come in, perform a function, and go away, which is what we see in combinational logic. But in rather, it goes in, and I'm going to hold it there as a statefulness until I needed to use it or until I need to change it. And that is the basis of what we're doing in registers and, quite frankly, in RAM. And we talked a little bit about the fact that both the register and the RAM is based upon this memory bit cell. And that memory bit cell is actually based upon this idea of a data flip-flop. And one of the things I want you to do is go through your reading assignments for this unit and kind of look at that flip-flop circuit. In fact, I would highly recommend using Logism, that you actually go in and build that circuit using Logism, the simulator, and play around with how it works so you get a real good sense of how it's actually allowing you to create the state, how it preserves the state, and how it allows you to change the state. Now, memory is extremely important in computer architecture, and as we're going to find out, what we find within the CPU is some key functions. So one thing, for example, we have is, and we've talked about this, is the ALU, or the arithmetic logic unit. We have, in most cases, some form of an I/O, so the ability to communicate with the outside world. We also have this idea of a control unit, and basically the control unit is essentially what is there to allow us to interact with these various other components and do so in a regular pattern dictated by the clock. So we have a clock, and the clock will trigger the program counter, and the program counter goes out there and fetches instructions in sequence. Now, what it does with them is one of the things we're going to want to look at, and where it gets them from is another thing we want to look at, because essentially these instructions, because this is what we're looking at in a von Neumann architecture, or the stored program architecture, if you would, is the fact that I'm putting both my data and the instructions that I'm executing in memory. So in order to get those instructions to execute, I have to go retrieve them from memory. Okay? In order to process things, I have to be able to manipulate, move them through memory. And sometimes that memory is random access memory. Sometimes we have what we call ROM, or read-only memory, although in many cases programs are actually mapped into a section of the RAM that we primarily read from. We also use a lot of registers, and again, registers are a place where we can maintain state. And one of the reasons this is important is that it's sometimes not possible for us to do all of the kind of operation that we need in one cycle of the clock. So I might need to retrieve a value and store it somewhere and then operate on it. And because I'm spanning cycles, I have to have places to keep this, because I can't do everything within a single cycle. And that's where this idea of a register comes into play and how I use it. Now, let's look a little bit at memory. Now, we talked a little bit about register, and the register was just a series of memory bit cells. Usually the width of it, or the number of cells that I have put together, is equal to the word size that I'm using in the ALU and the CPU in general. So in this particular case, we can see that I have 1, 2, 3, 4, 5, 6, 7, 8, I believe this is 9. No, 8. It's 8 bits. So every word in my memory has 8 bits. And every word also has an address. And what the address is just basically the position in the list that particular word appears. And each of these items is a flip-flop. That's a data flip-flop there. Now, if I have a whole series of them, for example, one whole group of 8, that basically is a register. And when I put this groups together in a long list, that's how I construct RAM. So, difference between RAM and ROM. We've talked a little bit about RAM. RAM stands for random access memory, and all that basically means is that I have an addressing scheme that allows me to go to a particular area of memory. So, for example, if I put this address in, I can go to this particular area of memory and retrieve that particular word. So, random in that sense that I'm able to access it directly, and I don't have to access it in some sequence. I kind of go directly to the one that I need, and I can retrieve it. And that's kind of the reason why we call it random access memory. Now, ROM stands for read-only memory, and really the only difference in this is that read-only memory, as a general rule, cannot be changed. So whatever I put in there, and oftentimes in some architectures where I'm not changing the program, I might put that program instructions in read-only memory. Now, in many cases, where we're actually putting the program's instructions is into a special area of RAM, an area that I don't access or change in the same way that I might access or change the rest of random access memory. So if we look at the whole processing of memory unit, we're going to have, in most cases, a bunch of memory in an array that we're going to refer to as RAM. You're also going to notice that we typically are going to have some registers associated with that. So in many cases, what's going to happen is it's going to take an instruction to move from the memory to some place. And so what we wind up doing is, in order to preserve state and to be able to maintain this information between ticks of the clock, I put a register in here. So what these registers refer to, or the MAR, is the memory address register. So when I'm trying to go fetch some memory, I might load a value and put it into the memory address register so that it can be acted on in the next clock cycle. So I put it here. I say I want to fetch memory from this particular address during the next clock cycle, and then I'm able to move it from there. The MDR is the memory data register, and it's the same basic thing. I might want to move from here into the register because it's very quick and easy to move from a register into the ALU, and so in that way I can actually preserve the state of what I read from memory across cycles of the CPU. Register, very simple. What are they? Data. The key thing is that data can be moved in and out of registers much faster than from memory. And the reason why is because with memory, I have multiple operations. I have to specify the address, then I have to specify that I want to move it and where I want to move it to. So it's going to take multiple cycles. Registers, on the other hand, generally are designed in such a way that they can access the ALU directly. So when I'm accessing with registers, it's very, very fast. Now, if we could in fact replace all of the memory with registers, it would be an extremely fast computer. This is not practical, however, because I'm still going to wind up in a situation where I need to be able to address and specify and get access to those memory cells, and it becomes very difficult to do that as the size of them grows. So I can't get enough space in registers as a general rule. Another element of this is that typically the registers themselves are sitting in the same space, on the same physical space as the CPU or the ALU and the other components. So where typically RAM would sit off on specially designed chips that you would access across the bus and then move it across that bus to our CPU, okay? The registers are actually right in the same silicon as the CPU. So its access is very fast because it's all within the same physical chip, but it's also very expensive because it's very difficult to put that much material, that many transistors on that CPU. So again, this becomes a little bit price prohibitive. Most modern computers, however, do have a lot of registers. In fact, a lot of modern CPUs are going to have both a large number of registers and something called cache. And what the cache is, it's kind of a like memory, but not quite. And basically what it is, it's essentially memory that's maintained on the CPU. So the objective there is it says I can get the data into the cache, and then it's faster to move from the cache directly into the CPU, so it can aid in processing. In fact, what normally happens there is that I will transfer a large number of addresses into the cache such that the CPU can fetch them and execute them without having to wait a couple of cycles to move that in from the memory. Now, looking at the way that memory is actually structured, there's two ways you can do it. There's a single dimensional way of addressing memory, and then there is a two-dimensional way of addressing memory. And in both cases, what happens is that I'm going to have some address, some series of bits that I'm going to put through a decoder. And what that decoder is going to do is it's going to, based upon that bit, identify the location and enable a group of memory cells. And the way that I'm actually going to be able to get access to the information in the memory is by enabling that group of memory cells using the address that I specify. And again, this becomes a decoder function. And the way that this works is kind of a single dimensional, which means I'm going to start at 0 and I'm going to go to some number. And I'm going to use the decoder to decode and select the appropriate line based upon the input into the decoder. The alternative to this, and the one that actually gives me a lot more capabilities in terms of the size of the memory, is a two-dimensional decoder. So I might have the same kind of an address, but it doesn't represent just a one-directional addressing scheme. It basically makes it two-directional, so that each of these boxes would have the full 8 bits of a particular memory location. So hopefully this has given you some sense of memory and how it functions, why it's important, what the differences are between registers and RAM, and a little bit about how we address it, either through a one-dimensional means or a two-dimensional means, as well as give you a little bit of a sense of why I need to have registers such as the MAR and the MDR, which would be the memory data register, and MAR meaning the memory address register.